Feel free to ask me any questions if you have any. We got about 4 more minutes before anybody's supposed to come. I'm just trying to pull some videos from my YouTube channel over to modules in here because I assume you guys have been looking at it, but from the stats that I get on the YouTube side, it doesn't look like as many people are using them as I'd hoped. So I'm thinking they might not realize they're there or whatever, but there's a lot of stuff to make up, for instance, for us missing last week, and that's one of the videos I posted and stuff like that. So there's one called the paradigm uh, for Gauss's law. That's something that you need to be able to do for the final. There's going to be another one as well for the inductance. It's going to be another quote unquote paradigm, a three-step problem process. And I'm going to teach you most of what you need for that today. Hmm. Ah, crap. Now it's time for class to begin. So I guess we better go ahead and get started, everyone. I will ask everyone again, does anyone have any questions before we get started? Actually, I didn't ask that before, but I told everybody you could ask questions. Oh, which chapters are going to be on the final? So what I'm planning on doing is my attempt will be to get through chapter 30. But chapters 28, 29, and 30 are going to be really short and skim. There's a lot of stuff I'm cutting out. So it should go basically from chapter 17 through 30. And like I said, with really, really strict adjustments of what I'm going to ask you of in chapters 27, or excuse me, 29, 28, 29, and 30. Anybody else? Thanks for that question, Ethan. All right, so what we need to start on now is basically the last thing we did was on 7/16, and then we had 7/18 was the day that basically the storm was too bad, so I couldn't cover anything. I posted videos in lieu of that, so you can learn how to do some of the stuff that we hadn't done. The last thing we had done is basically working on circuits. So the last thing was, in fact, let me double check what chapter number that is because I'm always forgetting these chapter numbers. Should have been chapter 26. And oh yeah, that's right. And chapter 27 was the one that I did via videos, but I'm going to quickly go through that as well, just to make some sense of it, if you will. So we'll start off with chapter 27, just because I need to make sure you know some fundamental things. So that's not the one I want. This is the one I want. Let's kill that. Okay. So what I'm going to do is start sharing your screen, and this is chapter 27. Uh-oh. Hold on a second, everybody. My pencil's gone from my iPad. That worries me. Oh, let this person in. Hold on, I'll be right back, everybody. Here it is. Sorry, everyone. I had to find my pencil. I was afraid my dog had taken it, but luckily I found it next to the couch, so I'm all good. Okay, so this is chapter 27. So let me start off by just letting you know that. And this is a quick review, quote unquote, review of chapter 27, because it's really not something we were planning on, I mean, that I hadn't already covered. I'd planned on doing that via video. So you supposedly already have that. Now if I can just get this real quick. All right. So I know I haven't shared the screen with you yet, so but that's okay. I'm getting ready to do something. Okay, so now I have that. So let me go ahead and share my screen with you guys. And this should bring it up in a second. Okay, so this is chapter 27, and as I said, this is a review of the important stuff from chapter 27. The main equations that you need are things related to the magnetic field and the force caused by the magnetic field. So first off, I want to tell you about a right-hand rule. If you imagine that we have a wire, say here, and it's very long, not bulbous like that. I don't know what happened, but anyway, that's as good as we can do, I guess. So that's a wire, and I'm going to say it's very long. So it's going to infinity that way. It's going to infinity that way. And remember, going to infinity just means it's going about 10 times further away than you are going to be close to it. So if we're 1 centimeter away, I want to make sure that end is at least 10 centimeters away from that part that we're 1 centimeter away from. Uh, a hundred's even better, a thousand's even better still, but that's what we're imagining. We're going to say that, in fact, this has a current I going upward. And what you want to think about is when you have a current carrying wire like this, you want to grab the current carrying wire with your right hand so that your thumb is pointing in the same direction as the current. So when when I grab this like so, then my thumb is pointing upward roughly like that. That means that right here to the right of the wire, the magnetic field is going into the board, because you can see that my fingers are curling around it. And what you have to imagine is my thumb is going in the direction of the current. My fingers are curling around it. And then you look and you say, oh, my fingers are actually rolling around counterclockwise. So then back behind, if we imagine this is a coordinate system that let's call that Y actually. And this is a coordinate system that we have it drawn here, and this is the Z axis, for instance. So if we get back here behind the wire, then the magnetic field is going to point this way. If we're to the right of the wire, it's going to point into the page. If we're to the left of the wire, it's going to point out of the page. And if we're in front of the wire, it's going to point to the right. So that's the right hand rule. That also means that's one of the right hand rules. That also means right here, if you drew a line straight from the center of the wire to a point between the x-axis and the negative x-axis and the positive y-axis, then you just draw a vector perpendicular to that, and that too is B. So you can see that basically B points this way, this way, this way, this way, this way. So basically you can imagine a circle of a certain radius, let's say, 10 centimeters. And the center of that circle has to be along the symmetry axis of the wire. In other words, the very dead center of the wire makes a long straight line. That's the Z-axis. We're going to align the circle that I'm thinking of such that its center is right on the Z-axis. And the plane that the circle is going to be drawn on is parallel to the XY axis. When I do that, then at 10 centimeters, you can draw a circle whose radius obviously is 10 centimeters completely around the wire on that plate that we're imagining is perpendicular to the wire. And what it says is that that 10 centimeter distance, the magnetic field is going to be the same strength at every point along that circle. And that strength can be given by B is equal to mu 0 I over 2 pi r, where r is the distance away. The mu 0 is a new constant. It's 4 pi times 10 to the negative 7th Tesla meters per amp. So as you can tell, we're going to use the unit of Tesla for the actual magnetic field. There's also a unit of Gauss. 1 Tesla, 1 T, is equal to 10,000 Gauss. So that's another magnetic field unit. And the Earth's magnetic field is on the order of 0.50 Gauss, okay, which is about 5 times 10 to the negative 5th Tesla. So that's some information that'll help, that should come in handy from time to time. Additionally, if you imagine the Earth as the circle right here, what we're going to do is picture this as our equator, and this is going to be North Pole, and down here will be the South Pole. What you can imagine, if you assume this is, for instance, the United States, and then it comes down around here, the Yucatan Peninsula, and there's Florida, something like that, somewhere in that kind of area. Well, what it turns out to be is somewhere right around in here, it's as if there's a bar magnet inside of the Earth like this. And here's the weird part. Remember, when we hold up a compass, the north end of the compass points sort of north. So that means this end is in fact a south pole and this end is a north pole. And I tell my students that magnetic fields are like seniors. They leave the north and enter the south. So the idea is, you've probably heard 1,000 times about older people, when they get older, they tend to move to Florida or something like that. So that's just a nice little, not necessarily completely accurate description, but it's a cliche of what elderly people do and seniors and stuff of that sort. But it works as a mnemonic to help us, because what we have to picture is the magnetic field of the Earth actually comes through, so we can say it actually goes, it's always complete loops, and it leaves the north end of the pretend bar magnet and then enters the south end. So that means this is the direction of that magnetic field on all these particular lines. And again, notice the magnetic field is leaving the north and entering the south, and that it doesn't technically disappear. It goes all the way a complete loop. And we know that that spot is basically in northeastern Canada. Okay, maybe not far north in Canada, but pretty far. So it's accurate. If you happen to be directly south of it, it's going to be very accurate. But as you can tell, when you're over in California, it would probably point a little bit to the east, and therefore have a wrong direction when you go to use a compass to navigate. So they sell maps that have exactly, for the area of the map, they'll tell you exactly which direction the magnetic pole points, or which direction points to the magnetic North Pole, and what the real north is to correct for it. So you can find out on your map. It might say like 15 degrees. You'll see a photo of it in this picture. But the main thing is, we need to understand these parameters, that a current carrying wire will carry a current. And if you lay your thumb along that wire in the direction of the current, and then wrap your fingers around the wire, that makes those fingers curl in a direction, either clockwise or counterclockwise, such that that's the orientation and direction of the magnetic field everywhere around it. And what I want you to imagine is, imagine a plane perpendicular to the wire, and on that plane, draw that circle that I told you about, and that circle should be centered on the center of the wire. That distance r is the distance from the center of the wire to the circle that you drew. And if that's the case, then the formula for the magnetic field strength at that particular location is mu0 times the current divided by 2 pi times r. Okay, you'll also notice that that direction, for instance, if I drew, let's say I drew a line from here to here, in polar coordinates, that would be like our R line for the coordinate R and the coordinate theta. This would be theta and this would be R. If you take a vector perpendicular to that R and going in the counterclockwise direction like this is, then what you'll find is that little vector is what we call the theta hat vector, which we'll make use of from time to time. I just need you to recognize that it exists, and I can even tell you that theta hat is actually supposed to be negative sine theta I hat plus cosine theta j hat. That's actually what theta hat is. And this r vector, we call that r hat, and that's cosine theta I hat plus sine theta j hat. You don't really technically need these, but it's at least nice to know they exist so I can refer to them and then not have to draw some special vector in hat and then say, well, this is in the hat and this is how it's defined. So if you think about the direction in which the polar angle theta increases, that's the theta hat direction. And if you think as a line coming from the origin, if you think about a line coming from the origin to any point in the XY plane, that's parallel to the r hat vector. So keeping that in mind, you could say, in fact, B points in the theta hat direction. So that's the beauty of it, is you can understand that no matter what radius you are away, it's going to point perpendicularly ahead of that by basically 90 degrees. So if you see here, this is the direction that the r hat vector goes. This is another 90 degrees in front of it. So any questions on that? Do y'all think y'all understand how the magnetic field around a current carrying wire how to figure out the directions for it? Does everybody get that now? All right, good. So I only got two of you, so can't do so much. But the main thing is, let me draw it now in a three-dimensional way that might be a little clearer, just in case there's some confusion. So we can imagine a rectangular plate right here, and I'm going to go over 2 and up 3, and then I'll know it's parallel to the other side, and then like this. And now I'm going to imagine my wire going right through the middle of this and extending straight upward like this, and extending straight downward like this. And then now you can imagine a circle around that. Oh, I should probably use a different color. I'm going to do a circle around that. Now it looks like an oval because we're trying to draw a two-dimensional or a three-dimensional circle on a two-dimensional piece of paper, and we have to tilt it to show that it's going off in the distance. So that's the actual circle. And you could, in fact, go a little further and say, okay, well, let's pretend, for instance, this is the x-axis. This is the y-axis. And this is the z-axis. Then again, if you take, let's say, this little line from the origin to here, that would be an r hat vector. That, in other words, that represents the vector that points radially outward. All I have to do is put that arrow on it. And then ahead of it, 90 degrees, is the theta hat vector. So you can see at each one of these locations, the theta hat direction is exactly the B direction. And as I said, B is equal to mu 0 I over 2 pi r, and it points in the theta hat direction, and r would be the radius of the circle from here to here. Okay, so that's really part of what we're going to do. Another thing we need to understand is that now that we know electric fields create current carrying wires, electric fields create currents. Current carrying wires create magnetic fields. So now that we know that, we want to see, how does something behave when it is in a magnetic field? And there's two major equations that we use for that. First off, the force on a charged particle in a magnetic field is given by Q times V, where V is the velocity of the charge Q. And you take a cross product of that with B, the magnetic field. And that is, in fact, the law that tells you what force is acting on a charged particle. Notice that if the velocity is zero, the force would be zero. Okay, so a charged particle just sitting perfectly still is not affected at all by a magnetic field. But if you start it moving, as soon as it starts moving, it's got a velocity, and therefore the QV cross B will come in. And what you'll see is basically, if you imagine that your hand is something like, well, let's try to draw it this way. I'm going to say, imagine this is my index finger. Imagine this is my middle finger. This is my ring finger, and this is my pinky. And then my thumb points up like this. And this is the index finger. And then this is my middle finger. Okay. Now, it doesn't look that much like a finger, but I could make it look more so just by doing this. Something like that. And you start to see the fingers looking more finger-like, right? And this would be, for instance, like that. And then this guy would be, of course, like this, and that. And then the thumb would be really crazy because it would go something like this. But the main thing we're trying to do with the thumb is to show that essentially that is perpendicular to the index finger. That's the key point. That has to be perpendicular to the index finger. Okay. So the reason why I did this is this finger should point in the QV direction like that. And then and it has to be straight, as does the thumb. So when you hold your thumb like your finger like this, it's got to be exactly like that, like you're doing a toy gun thing. Okay. This finger can move all around and do any direction you want. It just can't move past directly under the index finger, because then you might be double jointed enough that you can push your finger backwards like this, but that's not what we want. That's not going to help us. It's going to make things worse. Okay. So you only want it to be able to turn this way. In this case, this finger is supposed to point in the direction of B, going that way. And then F is perpendicular to both vectors. And F is also perpendicular to B. So that's how that right hand rule works. In this case, you point your finger in the direction of QV, you put your index finger in that direction. Then that allows you all these different locations and orientations of your hand, as long as your middle finger is lying along the line of Q times V. You can rotate it until finally you now have your hand in a position where you can bend your finger towards pointing in the same direction as B, or in other words, parallel to B. Once you have that, then the magnetic field is going to be perpendicular in the direction of the left hand, I mean, of the right thumb. Okay. So that's one big law. Now there's another one for a wire in a magnetic field. So that one is F is equal to I times L cross B, which looks a little stupid like that, but if you have an infinitely long straight wire and the current is I, then basically the vector force that is acting on the wire of length L is IL cross B. You might notice, for instance, that this right here, IL, has units of amps times meters, which equals coulombs meters per second. That, in fact, is exactly the units of this one, which is Q times V, and that is coulombs times meters per second. So you see that you have the same unit. That's why that equation works that way. But often we don't have a straight line. Sometimes we have a bent line, and we often don't have a uniform magnetic field. We often have a magnetic field that changes from location to location. When that's the case, then this equation becomes dF is equal to I dL cross B. And that's another one we use. So you really need to know these equations and these two right-hand rules. Okay. Anybody have any questions about those? All right, so let's look at an example. Let's imagine for a second that we have, I'm touching the wrong thing. Let's imagine for a second that we have a coordinate system on the surface of the Earth, and that this direction is due east, and this one's due west, and this one is due north, and this one's due south. Okay. And let's imagine that a electron has a velocity going straight up. In other words, it's perpendicular to east, it's perpendicular to west, it's perpendicular to south, and it's perpendicular to north. So this is the velocity v. So if you find that the velocity is v and the magnetic field points horizontally points to the north, so let's say b sub xy. In other words, the component of b that's in the xy plane, in other words, excluding any y components, points in the north direction. So can anybody use the right-hand rule that I just taught them about to figure out which direction the force will be acting? The law is F is equal to Q V cross B. And please recall that the charge is an electron and therefore has a negative charge. Anybody have an idea what direction this would be? Okay, so let me explain how to do it. It's perfectly fine. I literally just threw this on you, so I don't necessarily expect you to know it right off the top of your head. But first off, you got to notice, if you're dealing with a positive charge, then QV is exactly parallel to V, no big deal. If you're dealing with a negative charge, then QV is in the opposite direction of V. That's why I said an electron here. So what we're going to do is we're going to say this is an electron, so V is pointing up, maybe what we call in the Z direction. So since the velocity is in the positive Z direction, but the charge is negative, we know that the QV is in the negative Z direction. So it points straight down. Now I've got to take my finger with my index finger pointing down. I can put it in all these different positions, but I have to stop when I get to a place where I can adjust my middle finger to point it parallel to the magnetic field, which is due north. So when I do that, that becomes crap. It's focusing on my head instead of me. So that did not help very well. Okay. So when it's like this, we can see that now this middle finger is pointing into the page, which is the direction we call north. The index finger is pointing down, which is the direction we call QV. And therefore, since this middle finger is pointing north, this thumb must be pointing to the east. So the force would be to the east. Okay. So that's the kind of thing you need to do to make sure you can compute and figure out the directions of a force given a magnetic field. Now, you could also consider, a positive particle moving in the northward direction. Or since this one, we just use that to establish the XY direction of the magnetic field. Now, if we allow the electron to fly horizontally, say due north, then it could only be affected by a possible Z component of the magnetic field. So if I told you when the electron was traveling due north, it experienced no force, then that would tell you that the Z component is 0. So I'll say that if we learned that when the electron had a velocity due north, the force on the E minus is 0, then we can conclude the B sub Z is equal to 0. That means there's no positive Z component nor any negative Z component because the force was 0. Any questions on that? All right. What about, let's see, the same sort of scenario here. I'm going to do another north, south, east, west. So here's a east, here's a west, here's a north, and here's the south. And I'm trying to draw the letters a little bit distorted so they look like they're laying down on the board on the floor. I didn't do that with the east and west this time, but I'm doing it now. So the east should be like that, and the west is a little harder to reconcile, but like that. So there's our directions. Now let's imagine that the magnetic field, I need to get a different color. Let's imagine the magnetic field is pointing in the north direction again, because that's supposed to be what the magnetic field points when you're near the ground and near the North Pole. It should point basically due north. Now let's imagine that I have a positive particle like a proton, and its velocity is in the east. So this is a positive particle, and actually I guess I should draw that a different color because it's not standing out enough. Okay. Now, can anybody tell me in which direction will the force point? Ethan, Rylan, anybody, either one of you think you can do that?
I can guess, but I don't really
You
fully
want
understand
to
them.
Okay. Well, let's do it again then. Let's make sure we understand it. So in this case, it's a positive particle. So QV is definitely going to be the same direction as V. So I'm going to take my index finger and I'm going to point it due east, which is to my right in general, right? Now, the magnetic field's pointing due north. So my index finger being at a 40, my middle finger being at a 90-degree angle from my index finger is pointing in exactly the right direction of the magnetic field. They're both horizontal. You can see my finger going this way is horizontal. My finger going this way my middle finger is in fact going horizontal. And what I see is the force is in the upward direction. So in this case, the force would be in the upward direction. Okay. All right, another person. So let's try another one real quick. Let's imagine this time that we have a magnetic field. This is B, by the way. We have a magnetic field that's going to point horizontally to the east. And now I'm going to have a negative particle, and its velocity is to the north. Okay. This is north. This is east. This is west. And this is south. So now I've got a velocity of the negative particle going to the north, and we have a magnetic field pointing east. In which direction is the force?
Down.
The one says down. Let's check that out. So in this case, we've got QV, since it's a negative particle, QV is not going to be to the north, it's going to be to the south. And then because of that, my middle finger has to be in such a position where I can bend it in the same direction as B, but this thing's pointing due south. So I have to point it like this, where it's sort of horizontal like that. But now I can turn it up that way. And now you see my middle finger is pointing to the east, which is to my right. So now you see the thumb is actually pointing up. So this force is going to be up as well. I think you might have forgot that it was a negative particle. That might be why you got the force pointing down. So remember that what I advise you guys to do, if the charge is positive, then you just point your index finger in the direction of V. If the charge is negative, you point your index finger in the opposite direction as V. I'm saying V is in voice or vector. Okay. Then your middle finger has to be allowed to bend in the same direction so that your middle finger is parallel to the magnetic field, the B as in boy. Okay. It doesn't have to be exactly 90 degrees like this is. So it can be all these other angles, but the main thing is your thumb and your index finger and your middle finger are all mutually well, at least your thumb and your middle finger are your thumb and your index finger are perpendicular to each other. The middle finger can be perpendicular to those, but it's not necessarily. In this case, it definitely was, though. In both of these last two cases, the middle finger was in fact perpendicular. Actually, in all three of these cases, the middle finger was perpendicular to the thumb and to the index finger. So that's some stuff you need to be able to do and figure out. So make sure you work on the right hand rule for that. Make sure you're able to do the types of equations, use these equations that I gave you. So I'm going to restate them one more time. The equations we have so far are B is equal to mu 0 I over 2 pi r. And actually, I can't put a vector on that unless I have a diagram showing exactly where the current carrying wire is. I don't have that now, so I'm just going to tell you the magnetic field created by a wire uh, carrying a current I a distance r away from the wire has a magnetic field given by mu 0 I divided by 2 pi times r. And again, mu 0 is equal to 4 pi times 10 to the negative 7 Tesla meters per amp. The other equations we have is F is equal to QV cross B, and F is equal to IL cross B, but that only works if B and L is basically uniform. In other words, L points in one direction, the wire is long and straight, and the magnetic field is uniform. So you have to have a magnetic field that's equal to the same number at every point along the wire and points in the same direction. If that's true, then you can use that equation. If that's not true, then you have to use this other form of the equation that says dF is equal to I dL cross B. And then you can evaluate each little part on its own. Okay. One thing you want to know also, again, this is in the video, this is in the reading, when you cut a bar magnet in half, you don't make, a north pole and a south pole that are now separated. You actually just make two more magnets. And in fact, one magnet or each magnet has a north pole and a south pole. So if you were to take, for instance, a bar magnet that looked like this with a north pole here and a south pole here, and you cut it in two, then what you get is a north, south, like that. And in fact, that always turns out to be the case. And if we get too small, what happens is either the thing makes another magnet or the thing is no longer magnetized at all. Because of that, we have something equivalent to Gauss's law for magnetic fields that says the closed integral B dot dA is equal to 0. And that is the same as saying no magnetic monopoles. If we ever found a north pole by itself or a south pole by itself, then we have to go back and change this equation, which is one of one of Maxwell's equations. We'd have to go back and change it. And if we did that, then we'd find that it's quite a bit more complicated. But so far, we never found one. What we end up getting is del dot B. This is the differential form of that same equation, is equal to 0. So there's a way mathematically where you can convert this bottom equation into that top equation. And then there's a mathematical technique where you convert that top equation back to the bottom equation. But both of them give you, since they're equal to 0, tell you that there's no magnetic monopoles. The direction of the magnetic field is tangent to a field line at any point, and the number of lines per unit area is proportional to the strength. In fact, if you wanted to look at the magnetic field lines for this magnet right here, they never don't complete a loop. So they're always completing a loop, which means this guy would be like this, like that. And they're like senior citizens, as I told you. They leave the north and enter the south. So there would be another one right here, for instance. And that's some of the magnetic field lines for the actual bar magnet. Okay, notice I drew the purple through the inside so you'd understand that that field line goes all the way around. It's one continuous loop. If it's not a continuous loop, that's a very transient state and it's going to be disappeared completely in a few seconds, or it's not magnetism. Anybody have any questions on that? I've told you already about the Earth's magnetic field, how the North Pole is technically the South Pole, and how it's like a bar magnet is in the Earth. And I also told you that it's about a half a Gauss, and a Gauss is 1/10,000th of a Tesla. Your book talks about how to make a uniform magnetic field. The best way you can do it is take a really big bar magnet, as big as you want to have the uniform magnetic field. So if you wanted a circular magnetic field area that has a radius of 1 foot, then what you'd want is a 2 foot wide circular bar magnet. In other words, a bar magnet whose diameter is 2 feet, and you're going to put a north pole of that magnet, say pointing down, and then you're going to take a south pole of an identical magnet and put it below it and get them really, really close to each other. And what you then have is a uniform magnetic field. It would look roughly like this. So here's the big, big, big bar magnet, and this is the North Pole. And we're pretending like we can see through metal now. And then there would be a South Pole like this. And then the magnetic field lines would be basically straight down. Now, near the edges, they might wiggle out a little bit. But in general, if you stay in the middle, all the magnetic field lines are going to be the same. I'm drawing just along this edge, but in reality, it's everywhere. So that's how you make a uniform magnetic field. Okay. And if you want it more uniform, you just compress it so that the North Pole and the South Pole are even closer together, and you focus more towards the center. The closer you are to the center, the more perfectly uniform it is, and the farther away, the less uniform it is. Any questions on that one? Okay. So we told you that magnetic field, that current carrying wires create magnetic fields. I've told you that the magnetic field can even apply a force to a charged particle, given specifically by this equation. And the magnetic field can also apply a force to a current carrying wire of length L by these two equations. And of course, the wire with a current carrying a current I creates a magnetic field given by that. So those are all expressions we can use. And I'll leave the simple examples like you see in your book to you to work on. For instance, example 27.1. It says a wire carrying a steady DC 30 amp current has a length of 12 centimeters between the pole faces of a magnet. The wire is at an angle of theta equals 60 degrees to the field. The magnetic field is approximately uniform at 0.90 Tesla. We ignore the field beyond the pole pieces, determine the magnitude and direction of the force on the wire. So they're actually just saying that the wire, that the in the uniform magnetic field, which you might represent like this, you could say, okay, all these vectors are magnetic field vectors pointing out of the page. Notice how it looks like the tip of the head of an arrow. If you had them out of the page or into the page, they'd be little X's in the circle. So it looks like the little feathers on the back. Now, what they're saying with this is you imagine a wire. Oops. You imagine a wire like that. Well, a wire like that. I darn it, making me mad. Okay, so let's imagine a wire like that with a current I coming out of it. Okay, and a magnetic field B equals, they actually use 0.90 Tesla. And I'm going to say the current is I is 30.0 amps. Then they're also suggesting that this angle for the magnetic field is not this angle that you see here. That's not it at all. It's the angle that it makes with the magnetic field. But here you see the current is exactly perpendicular, and therefore the wire is exactly perpendicular to the magnetic field. So you could actually work it out straightforward. If you wanted to look at it from the side, though, it would look more like this. Here's your magnetic field lines. And then you could imagine the wire in this case being oriented like this, and this angle right here would be 60 degrees. And this right here would be the current I. So then F would be, we use the F equals Bill, and then of course you'd have to say sine 60 degrees. Okay, so that's meant to be F equals Bill. That theta is meant to be when the L vector and the B vector are tail to tail. So you can see, looking at this one, for instance, that the L vector is supposed to be parallel to the wire, and it's also supposed to be the length of the wire. So you could imagine this as the L vector. And you see that they are, in fact, tail to tail with B. That L vector is tail to tail with B, so you can actually just blindly plug that in and get the result. So now that we have that, we can do some more simple problems, but I think they're simple enough where you need not worry about them. So I'm going to actually draw a different one, and I am going to imagine that we have a series of circles representing a magnetic field like this. And it's supposed to be uniform, so I'm trying to draw all this about the same spacing and everything. And I'm going to say all these magnetic field lines are pointing out of the page. Sorry about that oval one there. No big deal though. So now let's imagine that we have a wire that comes up here, and then that wire makes a semicircle, which my program's just going to inherently make it into a parabola or something when I want it to be a semicircle. And then like this, what I'm going to say is that the current I is going that way, and therefore it's going that way, and therefore it's going that way. And what I'd like to know if this radius right here is R, and this magnetic field is B, 0 in strength, what is the total force on this piece of wire? So I'm going to break it up and imagine it having a part that corresponds to the semicircle and a part that corresponds to the straight line parts. So if I look here, remember IL points this way for this particular part right here. Okay. And then B points out of the board. So IL pointing up the page and B pointing out of the board means that my index finger points out of the page and the force is to the right. So I'm going to write right here that this is the force on the left part of the wire. And its magnitude is B0IL, where this distance is L. Now notice this distance over here is also L, and this current carrying wire is also carrying a current I, and the magnetic field is also a B0. So if we do IL pointing downward, then we've got to have my index finger pointing back at me because it's pointing out of the page. And that means this force points this way, and it is given by F right is equal to B0 I times L. So those two forces add up to give you 0. So those two parts don't contribute at all. what we want to do now is figure out what does the circular part do. So to make the circular part, I'm going to draw a coordinate system. That's going to be my x-axis. That's going to be my y-axis. And of course, my z-axis comes out of the board or out of the page. Okay. Now, this is where we're going to use that equation df is equal to idl cross b. Okay. So we need a DL vector, which is a vector that's parallel to the wire at a small little segment. Because remember, we're now allowed to have a bent wire instead of just a long straight one. So it has to be applied at a certain spot. So what I'm going to imagine is looking at this spot right here, which I've traversed an angle theta to get there. And then I'm going to traverse a slightly bigger angle beyond by allowing that theta to increase by a d theta. So the bottom purple line is at an angle theta, and the top purple line is at an angle theta plus d theta. And the reason I do that is because the DL now, I'm making that really, really small to make sure that I'm covering exactly the right amount. That vector right there is DL. And I think you can see from your formula S equals R times theta that this would be R d theta. And since I recently told you about the R hat vector and the theta hat vector, it should make some sense that this vector points in the theta hat direction, because clearly these little leg vectors that I drew first, the one at theta and the one at theta plus d theta, those are actual R vectors, and you can see the d theta is ahead of it. So now I'm going to say that f is equal to the integral of df, which equals, I'm going to go ahead and pull the I out in front because that's a constant. It's going to be equal to the integral of dl cross b. Okay. Now notice the z is out of the page, so that tells us that b is equal to b0 k hat. So now I can put all this in and say I times the integral of r d theta hat crossed with b0 k hat. Well, that gives me, since the r is a constant and the b0 is a constant, I can pull that out in front. And since the cross product is what we call a linear operation, I can pull the b0, the d theta, and the r theta all out in front and just let the cross product do what it's supposed to do. So now I have I times b0 times r times the integral d theta of theta cross k hat. Okay. Now, if you look at theta cross k hat, theta is basically that little purple vector that I have written in purple and say it's equal to DL. That's the theta hat direction, and the k hat direction is coming out of the board. So if I wanted to do a cross product for that, I put my index finger parallel to the little DL vector, and then I put my my middle finger pointing out of the page, and that should give me, that's DL, that's d theta, theta hat cross k. So that actually suggests that that's weird. Hold on. DL cross B. Oh yeah, that's right. Okay, so that actually suggests that when I do that cross product, my thumb is now pointing parallel to the R hat vector. So it's pointing radially outward. So you could actually imagine it as if it is, let's use another color, let's say green. This direction is the direction of theta hat cross k hat, which is actually equal to, say, r hat. Okay. Now, what you see is we're going to have to integrate all this stuff. And in so doing, we're going to integrate, and you can see that on the right half of this, let's use some red here to show you what the components are. I'll use pink. You can see that this one clearly has a negative x component and a positive y component. When you get over here, though, you'll have a DL that way, and you'll still have a d theta cross k hat, gives you that same vector that's in the r hat direction. Okay, but now you see that it's going to have a negative x component and a positive y component. So I think from the symmetry of all of this, you can tell that the x components are going to cancel out because I have a negative x component. In fact, it'll be all x at theta equals 0, and it'll get smaller and smaller x component until I get to the y-axis. And then once I go past the y-axis and get in the second quadrant, you'll see that the x component is now negative, and it gets bigger and bigger until it gets to theta equals 180, at which time it's all x again. So that tells you that by symmetry, the x components are going to cancel out, and therefore we just need the y components. So that's what we've got to actually do with this one, is we've got to calculate the y components. And the y components would be given by basically d theta times the sine theta. So this part is going to become, well, actually I can leave that k off. It's going to become sine theta after we do the integral part. So we can now say this is going to be I times B0 times R times the integral of sine theta d theta from theta equals 0 to pi, actually, like that. And of course, the derivative of cosine is negative sine. So the integral of sine is negative cosine. So I'll get I B0R times negative times cosine pi minus cosine 0. And the cosine of pi, of course, is negative 1. And the cosine of 0 is 1. So we got negative 1 minus 1 is negative 2. So I'm ultimately going to get 2, and the negatives cancel out now. So it'll be 2 I B0 R, and that force points purely in the j hat direction. Okay. So if we added up all the forces, if we add the FL, the F and the FR, and then this F, we're going to get just 2 IB0R. And that's a typical problem you have to be able to do. Anybody have any questions on that one? And actually, I shouldn't call that sine theta. Let me say that all this, I'll do it this way. I'm going to erase this sine theta here. What I'm going to say is theta hat cross k hat actually gives us r hat. And r hat is cosine theta I hat plus sine theta j hat, like that. So what I did was I ultimately said, well, the I components, the cosine theta part, that's never going to appear because symmetry is going to make them go to 0. So that part integrates to 0. So all I'm really going to do is say that theta hat cross k hat gives me sine theta j hat, which is what I actually put in here. Okay. And then of course I added the j hat to it as well. So I could write j hat, and that's why I got that. Any questions on that one? So the downside of using that R vector is that you sometimes have to break it down into cosine theta and sine theta. So while we're looking at that, let me go ahead and show you how trivial that is so you won't be scared of it. But if you take a typical coordinate system like a x, y, and we just think about polar coordinates, which is something you have covered, at least in trig, then we can imagine, for instance, having a position in space that is that point right there. Now that point corresponds to x, y, because that's x and that's y, right? So that point is x and y. But if you make that line's length r and you make this angle theta, then you could also call it the point r theta using polar coordinates. Now, if you tried to figure out what x is using trigonometry, you could realize that the trig functions give us cosine theta is equal to adjacent over hypotenuse. So that's x over r. And you'd see that sine theta gives us opposite over hypotenuse. So that's y over r. So now you can see that x is going to be equal to r cosine theta, and y is going to be equal to r sine theta. So if you want a r vector like that, then it's clearly going to be r cosine theta I hat plus r sine theta j hat. But if you want a unit vector, you have to divide r vector by its magnitude, which I think you can see that that's going to be r. And then you, of course, get cosine theta I hat plus sine theta j hat. And then as an extra little wonderful piece, dr d theta is actually equal to negative sine theta I hat plus cosine theta j hat, which is exactly theta hat. So that's a good way to remember theta hat. But you can also work theta hat out because lo and behold, we know I can put another x-axis here. I can put another y-axis here. I can go up an angle theta, and then I can go ahead by an angle 90 degrees in front of that. That is my theta hat vector. Now, from this, you should be able to tell that this angle right here is 90 minus theta, but this angle right here is theta again. So if you wanted the x component, let's do it in this fancy pink. If I wanted that x component, this is theta hat sub x. That's just going to be, and notice the length, by the way, is just 1 because it's already got the hat on it. So the length is 1. That's what that hypotenuse is. Okay. So the x component of theta hat is clearly going to be the negative of sine theta. Okay. And the y component of theta hat is clearly going to be cosine theta because you can see it's right here. And we already said that this, of course, is theta. So yeah, you do get cosine theta minus sine theta for the theta hat, and that's exactly what I found. So that's what those vectors are. You have to sort of use them a little bit to play around with them, but you can also find other ways by just realizing that the cross product picks out components of vectors that are perpendicular to one another, whereas the dot product we used to use or we've used in the past picks out parallel components. So that's why we use them a lot of times in physics. The dot product for instance, is used in work because we want the component of force that's parallel to the displacement. And then the cross product works for the torque because we want the component of the lever arm that's perpendicular to the force, or the component of the force that's perpendicular to the lever arm. So that's a major problem, and that's probably the only really quote unquote hard problem. What I will tell you is that some simple things come out of this. So for instance, if we take Newton's second law, the summation of the forces is equal to M times A, something like that. And we imagine, for instance, that there's a magnetic field that's uniform right here. And we imagine, for instance, let's say a positive particle with a velocity v that way. It's entering this magnetic field. Since it's a positive particle, v and qv both point to the right. So v is parallel to qv because q is greater than 0. And then my index finger pointing to the right allows my hand to be in all these different positions, but I have to choose the one that allows me to point in the direction of the magnetic field, which is out of the page. When I go to do that, that means I have to turn my hand completely upside down like this. Okay. Now you see my thumb is actually pointing out. Let's look at it. It's like, now you can see my thumb when my middle finger is pointing out of the page like it is here, my thumb is now pointing down. So this tells us that the actual force is perpendicular this way. So you might imagine, for instance, it's going to pull it perpendicular, and that's going to make it rotate, or that's going to make it curve. And that's exactly what happens. In fact, if you look over here, once the velocity has been turned so that it's this way, now you do a QV that way and a V out of the board, and you see again, you get the force is that way. So what that's telling us is that the force is always going to be perpendicular to this velocity. And if this area with the uniform magnetic field is large enough, this thing is going to complete a circle. And of course, we know that the acceleration required to maintain a circle is v squared over r. So now I can take q times v. Well, let's put it back in blue. I can now take q times v times b. They were all perpendicular to each other, so the sine theta just becomes a sine of 90 degrees, which is 1. So that's the whole left-hand side force, qvb. The right-hand side is going to be m times v squared over r. So from that, you can see that this exponent of 2 and this v cancels out, and we're going to get that r is equal to mv over qb. So this is an equation that your book gives you and works out for you, but that's basically the radius of the curvature of a charged particle moving in a magnetic field. Now, if the charged particle actually had a magnetic field, or excuse me, had a velocity component that was parallel to the magnetic field, so instead of it just coming to the right, maybe it's coming out of the page a little bit or into the page a little bit. Well, that particular component is not going to be touched by the magnetic field at all. So there's no force is going to apply to that. So that's going to stay constant. So let's imagine let's say the out of the board component of the velocity is 2 meters per second. Then every second it's going to move 2 meters out of the plane of the paper. And you then could actually figure out, well, how long does it take to complete one circle? That would be called the period. And to do that, we know that v for a circular motion, v is equal to 2 pi r over t, the period. So if we plug that in, we could say R is equal to M times 2 pi R over Q times B times T. You can immediately see that the R cancels out, and you could ultimately get that T is equal to 2 pi M over QB. And that, lo and behold, is the period of the particle. In other words, that's the amount of time it takes the particle to complete one circle. So if that happened to be, for instance, 2 seconds, and the velocity parallel to the magnetic field, that component was 2 meters per second, then it would go 4 meters out. So you would have a circle that's like this, but it started back here and ended up 4 meters out of the paper. And the next circle would be another 4 meters out of the paper. And in fact, that angle that it covers is called the pitch of the helix. So that's how you make, for instance, threaded rods and stuff like that. Now, we also have our other rules. Remember that period is 1 over the frequency, or frequency is 1 over the period. Both of those are, both of those are valuable equations that we're going to use. So now I can also say that since I know the period, F is equal to 1 over the period. So that's going to be QB over 2 pi M. So that's another equation we can use. And all of this is the stuff that helped us discover a way to create a particle accelerator. And what was done was we had a thing called the super Ds or the double Ds, which were semicircular cavities like this. And each of them had a radius, say, R, like that. And since the frequency doesn't depend on the velocity at all, since that's the case, what we can do is just set the frequency to the right value for the given charge and the magnetic field strength we're using. And we can start a particle going like this. And when the particle gets right here, say, right at this edge, we can make sure that this side is negatively charged. And what's going to happen is, as soon as this particle gets in that little gap, it's going to be accelerated because it's going to be positive on this side and negative on the other side. It's going to be accelerated across this. So it speeds up a little bit. And then when it speeds up, now it's going to come back here and do a loop like that. But since it's faster, the radius is slightly larger from this R equals mv cross B. Now, when it gets over here, it's going to change this so that this one's negative and this one's positive. So when it gets to this gap, it's going to accelerate again. And come out over here. And now it'll make a bigger circle. And then it'll get accelerated again through here and make a bigger circle. And again through here and make a bigger circle, and again through here, like that. And when it's all said and done, you can just make sure this misses the last thing and send that particle on with whatever speed. That's how we made the first cyclotrons and the quote unquote atom smashers. But it was all because that frequency didn't depend on the velocity. That allowed us to just rapidly change the frequency, or change the polarity of the 2Ds according to the frequency formula. And then that would automatically just speed up whatever particle we had for the magnetic field we had. Any questions on that one? Okay, so I've sort of given you a rough outline of everything you have to do in here. Your book does talk about the aurora borealis, and notice that thing I told you about with the charged particle, like the positive particle here, if it had a velocity into or out of the page, that one would be totally unaffected because it's parallel to the magnetic field, and cross products don't work on components of vectors that are parallel. So it's going to just keep helixing out. So that's exactly what happens to the basically the solar radiation that comes from the sun, obviously. That's made up of charged particles, and they hit our magnetic field, and they tend to spiral around the magnetic field lines, and they tend to also have a velocity parallel to the magnetic field. So the positive one will head one direction, maybe to the North Pole, and the negative one might head to the South Pole. Of course, it could also be in such a way that they head other directions. But the main thing is they're going to spiral around the magnetic field lines, and the magnetic fields get stronger and stronger as they approach the north pole of the north magnetic pole of the Earth and the south magnetic pole of the Earth. And what happens is those electrons come in with so much energy, they can actually ionize the air. And that ionization allows little photons to come off of various colors. The colors are indicative of basically the energy differences between the molecules in the air with the electron in one orbital compared to the other orbital. Each of those has a very unique energy, and that energy can be set equal to hc over lambda, where lambda is a wavelength. So you get these really pretty colors. This happens, like I said, near the north magnetic pole, and that's called the aurora borealis. And then it happens because boreal means north in Latin, aurora means dawn. So they sometimes just say light or prettiness or something like that, but aurora means dawn and boreal means north. Additionally, the South Pole near the South Magnetic Pole has it as well. And in that case, it's called the aurora australis. And that's because the Latin word for south is australis. So that's basically it. We've covered all the different stuff. We can talk about a velocity selector, for instance. That's another neat little thing. If you had, for instance, a positive particle here going through here, you could subject it to an electric field by running it through a parallel plate capacitor like this. And that, of course, would mean the electric field lines are this way, and that they're going to compel the positive particle to turn up. But what we did was we allowed this positive particle, I'm actually going to take off all that. We allowed this positive particle to come in through a itty bitty slit. So what I'm going to do is put a little line back here and just an itty bitty slit like that. And that little slit is what lets the particles through. And we're going to have, like I said, a positive particle through here, and it'll have a bunch of different velocities. Okay. But what we want is only very specific particles that have a very specific speed. So the way we can do that is we can create yet another slit on the other side, exactly in line with the first slit and exactly as thin as the first slit. So that's what we're shooting for here. And to do that, what we're going to do is submerge it into a magnetic field as well. So the electric field, as I said, pointed this way because it's the direction a positive charge tends to go. And what we want, that's actually the direction of the force as well. What we want is a magnetic field that's going to cause the positive particle to move in the downward direction. So QV is definitely to the right because the charge is positive. So I'm going to say QV is that way. And what I want is the force to be down. So what I'm going to do is turn my hand this way so that my thumb is down. And what I see is the magnetic field has to come out of the page. So now what I'm going to do is I'm going to say we also have a magnetic field that's uniform this way. So what happens here is you expect some deviation for the positive particle that way due to the electric field, and you expect some deviation this way due to the magnetic field. But if you have them two cancel out, then QE, which is the force due to the electric field, and QVB, which is the force due to the magnetic field, if you set them equal to each other, you can see that the actual charge cancels out. You get the Q is like that, and it cancels out. And what you find is that this will automatically give us a velocity that's equal to E over B. So this is our velocity selector. So if you want a velocity, you just have to express it as an electric field divided by a magnetic field. It'll automatically work out to the right units. And then you make your electric field and your magnetic field match those values. And then you make sure they're in this direction and you set up this little slit. And the only thing that's going to get through is particles that have exactly that velocity. So that's another neat thing that's helpful. Something else that happens is the Hall effect. So if you imagine a wire like this, there's two things that could possibly be happening. You either have a positive particle that's going this way for a current going this way. That's what we call conventional current, is positive particles moving in the direction of the current. Now, what we also know is that could actually be, in reality, negative charges. And if the negative charges are really doing the work, then they would be going this way, and that too would create a current going to the right. So if you actually set up a magnetic field such that the magnetic field is, let's say, into the board, I think that'll work. Yeah, that'll work. I'm going to set up a magnetic field into the board just because I haven't drawn one of those. That's why I wanted to do it that way. So let's say that, skip to, skip to, skip to, skip to. Okay, so now I picture this magnetic field. Now, QV for the positive particle is definitely to the right. The magnetic field is into the page. So I turn my hand, instead of like this, I turn it like that. And I see that the magnetic field going into the page tends to make this positive particle go that way. Okay. Now, if I do that with the negative particle, remember, QV for a negative particle is the opposite direction of V. So again, I'm going to point my finger to the right. The magnetic field is going to be into the page. So again, I get a force that points up. So now if you take a multimeter, let's say we have a nice little multimeter like this. Got a nice little screen displayed here. We've got it set on voltage DC. We're going to have a red terminal right here, which is the V omega terminal. And we're going to have a black terminal right here, which is the COM terminal. And what we're going to do is we're going to take our red wire and run it over here, back here, and then touch it on the top of this wire. Then we're going to take our black wire, run it over here, and then touch it right there. So if there's positive particles, let me write it this way. If the current is carried slash is by positive particles, then the top of the wire will have a net positive charge and be at a higher voltage than the bottom. Okay. What actually happens, according to experimental evidence, is that this actually reads a negative, let's say, 0.50 volts. Okay. So what that tells us is in reality, we actually get a series of negative charges lining up all along the top when we do this Hall effect. And you get a series of positive charges all down here. And that's called the Hall effect. So that Hall effect once and for all told us that, oh, it's clearly negative particles that are moving. And that's what I wanted you to know about that. You know, I don't generally give you problems to solve on that, but I do want you to understand it. And of course, you can see how the forces, obviously the Hall force would be basically QVB. And that's going to actually make a voltage difference from the top to the bottom. And you can assume that electric field is actually a uniform electric field across the wire. And therefore, the voltage difference between the top and bottom will be the electric field times the diameter. So you can use that. That's how your book does these equations that it gives you for the Hall effect. But like I said, I'm not requiring you to do any of that equation work. The last thing I want to point out regarding this is just like we had electric dipole, P, and that was defined, for instance, as a positive charge and a negative charge, and a vector that points from the center of the negative charge to the center of the positive charge, in other words, the opposite direction of the electric field that's created, then the dipole moment P is equal to, since this is negative Q and this one's positive Q, it's just Q times the D vector. And because of that, we discovered that torque is equal to P cross E, and potential energy U is equal to, actually, forget the integral part, it's equal to negative P dot E. Well, guess what? There's a magnetic dipole, and it's given the symbol mu. And in fact, what it is you can treat it like it's a loop of wire. So let's say this loop of wire has a current I going around it in this counterclockwise direction. Then, according to the right-hand rule, the mu vector would be that in that direction, and mu is actually equal to I. Notice I left a space, that's on purpose. So it's I times the area in that circle. So I'm going to change colors real quick and just say That's the area that we're talking about. So that's what the magnetic moment is. And I'll just say in the n hat direction, just because I need a direction that's perpendicular or normal to the actual loop of wire. So I'm just going to say that's the n hat direction. But the main thing is if I had more than one loop of wire, then the magnetic moment would be N times, where N is the number of wires, I is the current going through each of the wires, and A is the area. That's called the magnetic dipole. And lo and behold, torque is equal to mu cross B, and potential energy is equal to negative mu dotted with B. So these are new equations that you have to be familiar with. Any questions on that? All right, let's take a break till 7:10, and I'm going to do some really quick stuff with chapter 28. And next time will be our next meeting. So go ahead. I'm right here. You can feel free to ask me questions. It's only you here now, Ethan. Uh, but anyways, you're certainly welcome to ask questions if you have any.
All right. As far as homework goes, we need to finish through 30, right? On the my lab.
Uh, in some sense, but let me tell you something that I don't get to tell everybody, and I make sure I don't tell everybody in the beginning. So if I look at your grades and your test scores and your lab scores are all pretty decent, and your homework scores bringing you down even the least amount, at the end of the semester, I throw your homeworks right out.
All right. Well, I think I'm gonna do them anyway just to get the practice in for
Yeah,
the
that's
final.
good. That's good. But what I would say is the most important thing is doing well. Have you already done well on your face-to-face tests that you've been taking?
I've done well on 2 out of the 3. I'm gonna redo one and it should be better. So I'm
Okay.
not too worried.
Oh, if you, yeah,
I've
if you
done the I've
that
done
doing
the
that
you
well,
had the sheet.
right?
You have the sheet where you can fill everything out, and I'm ending fine, but I'd like to get that one test score up a little bit.
Well, given that, then this might not apply to you. But if you're really stressed and want to make sure you do well because you're worried about your grade, a lot of students use the homework to bring their grade up, and that's the students that I won't take out their homework. But when
Hmm.
students are being pulled down by their homework, I will throw it out. Uh, in that case, the most important thing is that you do as well as you can on the final, because if you get like a, let's say, a 77 on the final, that's a high C. 75 is a mid C, 77 or higher up to a 79.4 is a high C. If you got a 77 on the final exam and I calculated your grade and it came up to be an F, I would give you the C, because
Hmm.
it's a comprehensive exam, and I, make it hard like that so that I have that freedom, and you showed me that you peaked perfectly. If you had an 87, I'd give you the B. If you had a 97, I would give you the A. So
That makes sense.
yeah. So what I normally tell students is focus really a lot on taking the practice tests over and over and over. If you find
That's
a
what I'm doing.
Yeah, if you find a certain chapter gives you some difficulty, then try some of the chapter tests that don't count either way until you get up to speed on that, and then go back to doing the practice tests again. But it sounds like your grades are good, so you're probably not going to have to worry too much about it either way. But yeah, if you do your homework grade, that'll give you even more padding on how good you're doing going into the final.
Yep. Yeah, my homework's probably in the 90s right now, so I'm not too worried about that.
Excellent. Good deal. All right. Well, your your next chapter that we're going to cover now is chapter 28. And I'm really getting a couple of things out of here. One thing, for instance, that I didn't mention on the previous page, or I mean, on the previous chapter, and I should have, is that, one wire can cause a force on another wire. So we really should know exactly how to calculate that force. So I'm going to give you a quick rundown on how that occurs. Let me get back to where I was. I was about to run out of pages. So we know that the force on a wire is given by IL cross B. Well, what happens if you have one wire with a current I1 and a length L1, which is very, very long, and then you have another wire, let's say one that has a current I2 and a length L1 as well. You might wonder, do these two wires attract each other, or do they repel each other, or are they totally unrelated? Do they not affect each other? It turns out they actually have a force on one another. So what I do is calculate the magnetic field at wire 2 due to wire 1. And what I'm going to have to add here is that this is a distance d apart. Okay. So B, and this is caused by 1, and it's on 2, so I'm going to call it B21, is equal to mu 0 I1 over 2 pi times D. And notice that means the magnetic field that I'm talking about here is actually pointing into the page at that location where the green wire is. Okay. So now we use F equals IL cross B to compute the force on 2 due to that magnetic field. Oops, that went really ugly. Okay, so according to this, notice the IL is perfectly perpendicular to B. So we really just get F. Well, actually, I'll do it in black like I was doing before. We get F on 2 due to 1 is actually equal to current I2 times L1, because it's L1 slash 2, because they're both the same, times B21, which equals mu 0 I1 I2 over 2 pi D times L1, so that we can say the force per unit length is equal to mu 0 I1 I2 over 2 pi D. And what you can also figure out from this is what is the actual direction. And you'll see that when you have an IL pointing up, that's a vector. Okay. So I use my index finger to point up, my thumb's still doing the right hand rule thing. And then I use my middle finger to point in the direction of the magnetic field, which is into the page. So I see that, in fact, this force, actually, I should use black. So I'm going to do that. This force is this one. That's the force on 2 due to 1. So you see that parallel parallel currents attract. Anti-parallel repel. And the formula is given by that. So that's just one thing I wanted to hit on for you guys. Now what I'm going to do is show you two equations, and I'm going to show you the hard one first. And this is called the law of Biot-Savart, or the Biot-Savart law. That's BIOT hyphen SAVART law. Now, what it tells us is that the differential magnetic field dB is equal to mu 0 I over 4 pi times dl cross. Now it's going to be an R vector from dl to p. And then all that's got to be divided by that R vector from dl to p magnitude cubed. Now, it would be a 1 over r squared law, but what you really want for that r on top, you want a unit vector. And to make a unit vector, you take a regular vector and divide it by its magnitude. So that's why I have a 3 down there instead of a 4. Now, let me show you in a diagram what we mean by this. So if you imagined a current I coming out of here, then you might imagine, for instance, a dl vector, which is tangent to the wire at a particular point, okay? And then you also might imagine there's a spot in space where you want to know exactly what the magnetic field is. Okay, well, what you need is a vector. I'm not going to use that color. What you need, what you need is a vector. Looks like somebody else is coming in. What you need is a vector from L to P. So that's the R dl to P vector. So that's one way of writing it. What I normally do, though, is I imagine a coordinate system. That's X, that's Y, that's Z. And then I say, okay, well, there's a vector that points to DL, and that's called the vector RDL. And then there's a vector that points to P, and that's called the vector RP. Then R dl to P is actually equal to RP minus RDL, like that. So that's two ways of interpreting it. And then you just say, well, dB is equal to mu 0 I over 4 pi times dl cross RP minus RDL over the magnitude of RP minus RDL to the third power. So that's the law of Biot-Savart, and I need to show you how to do that. Okay, so let's do an example. I'm going to use my black pen to draw a coordinate system. And what I'm going to do is say that this axis coming out is the x-axis, this axis on the page going to the right is the y-axis, and this axis on the page is the z-axis. And now what I'm going to do is imagine that I have a wire that's infinitely long and parallel to the z-axis. Okay, I'm going to further imagine that the current I is going up, and I'm going to say, I think I might want it. Yeah, that's cool. I'm going to say this is the point P at which we wish to know the magnetic field. And I'm going to say the distance from here to here is actual R. And the reason I'm doing that is by symmetry, I could rotate this coordinate system by any angle, and I would get, leaving that spot right there, that P spot right there, it would no longer be on the y-axis. In fact, if I rotated it by 90 degrees, it'd be on the x-axis. If I rotated it by 180, it'd be on the negative y-axis. If I rotated it by 270, it'd be on the negative x-axis. All of this means it's always going to point in a direction perpendicular to the line that connects it to the wire. So it really is behaving in as if it's a point in the theta direction. So that theta hat stuff will come into play. Now, what I'm also imagining, as I said, was this goes on for infinity that way and that way, of course, as well. So I'm going to imagine a little bit of differential line element, because what we know is the formula is dB is equal to mu 0 I over 4 pi times dl cross rp minus rdl over rp minus rdl cubed. Okay. So this little guy that I have right there with the little blue mark on it, that is my little DL vector. So I'm going to imagine this is a little vector DL, and that vector DL is just DZ hat. Now I also have to draw a vector that points from the origin to it, and that's that vector right there. That vector is called RDL, and you can see it's actually got a length. Since it's parallel to the z-axis, you can call that length z, and it points in the z positive direction. So I'm going to call that r z times k hat. I also have a vector rp, which goes from the origin to the point P at which we wish to know the magnetic field. And that vector is RP. And you can see that one is R J hat. Okay. So now I've completed my RP and my RDL, but I need to calculate RP minus RDL now. And you can see that's going to be RJ hat minus Z K hat. So that's what that RP minus RZ is. Now, if you look closely, you can also see that that vector is really this vector, the RP minus RDL. That's the RP minus RDL vector. And I think you can tell from that that the magnitude of the RP minus RDL vector is going to be equal to the square root of z squared plus r squared. Does that make sense, Ethan and Bruce? So now I can go ahead and compute. I'm going to do it in black. So B is equal to the integral of dB, which equals mu 0 I over 4 pi times the integral of, now dl we said was dzk hat. Now I've got to cross that with rj hat minus z k hat, and then I got to divide all that by z squared plus r squared to the 3/2 power. Okay. Now, if you actually take a cross product of DL, which points up, remember you use your index finger for the first vector in the cross product, and then RP minus RDL, which points diagonally down at that direction, okay, you see that RP cross that points into the board. So the cross product gives you a direction that's technically negative I hat. So when I say, I'll write it here, note DL cross RP minus RDL gives you basically a negative I hat times some stuff. Okay. But the main thing is the direction's in the negative K hat direction. And that's what I was telling you. It's always perpendicular to the vector that points uh, from the center of the wire to the point P where you wish to know the magnetic field. Well, that vector is specifically an R vector, like an R hat. And then 90 degrees in front of that is a vector that we know of as theta hat. So this is fitting the bill. It's just we happen to be doing it in Cartesian coordinates, but the symmetry allows us to do this for any particular angle. So we ultimately get that it's going to be in the other direction. So now what I can do is I can actually do the parts of the integral as it's shown here. What I can do is take the dz times the rj hat minus zk hat. All of this is basically going to be the magnitudes first. So in this case, I'm going to say b, let's go back to black. B is now equal to mu 0 I over 4 pi times the integral. What I'm going to do is pull out all the constants out in front. Now, remember the magnitude of RP minus RDL, this guy in the numerator, is just square root of z squared plus r squared. And what you might notice also is that we're going to consistently have a k hat crossing an rj hat and a k hat crossing with a k hat, and you can see that that's going to be 0. So for instance, when I say dz, actually let me do it like a sidebar. I'll do it over here out of the way. So let's say dzk hat crossed with rj minus zk is equal to dzr k hat cross j hat plus, or minus, I should say, because there was a negative sign in front of the z. So I'll say minus z dz. And now I'm going to have k hat cross k hat. But k hat cross k hat is 1 times 1 times the sine of 0 degrees, which is 0. K hat cross j hat is in the negative I hat direction. So this one's going to be negative I hat. And that's all we need. So now I can rewrite this DL cross RP minus RDL is just going to become DZR with a negative sign and an I hat. Okay. And then all that's going to be under Z squared plus R squared to the 3/2 power. So I'm going to say let Z equal to R tangent theta, then dz is equal to r secant squared theta d theta. So when I do that, I get b is equal to negative mu 0 I over 4 pi. I can go ahead and pull this r out in front. and I get the integral of dz. Oh, excuse me, we already figured out what dz is. Dz is going to be r secant squared theta d theta. And now what you're going to see in the bottom is, since z is equal to r tangent squared theta, I'm going to get r squared times tangent squared theta plus 1, and all that raised to the 3/2 power. Now, what I have is that r squared in the bottom being raised to the 3/2 power is basically going to make it r cubed in the bottom. And I have a r squared in the top because those two r's that are there. So this is going to become negative mu 0 I over 4 pi, just plain r, because the r squared in the top cancels out with the r cubed in the bottom, leaving just an r cubed, or leaving just an r to the 1 power in the bottom. Now, tangent squared is, our tangent squared plus 1 is secant squared. So I can replace this all with secant squared theta, and that becomes secant cubed theta in the bottom with a secant squared theta in the top. So I'm now going to have the integral of d theta over just plain secant theta, which is basically the same thing as cosine theta in the numerator. So now I can say, oh, and I also left off the I hat vector, so I'll put my I hat right there. I'll put my I hat right there. And now I have B is equal to negative mu 0 I hat over 4 pi r, and we're going to take the integral of cosine theta d theta from theta equals 0, actually from theta equals negative pi over 2 to positive pi over 2. Now I could, since cosine's an even function, I could replace this with 2 times the integral and just integrate it from 0 to negative 0 to positive pi over 2. That works as well. So let's just go ahead and ignore that part and just say that I can do it if I wanted. So this is going to become negative mu 0 I over 4 pi r. Now the derivative of sine is cosine, so the integral of cosine is sine. So this is going to be sine of pi over 2 minus the sine of negative pi over 2. And of course, the sine of negative pi over 2 is basically -1. Yeah, the sine of pi over 2 is 1. And the sine of, yeah, that's right, because sine of pi is 0. So this one's going to be 1 minus -1. So that's going to basically give us a plain factor of 2 with an I hat. So I now get negative and actually it's sine minus negative plus is 2. So yeah, it's going to be negative mu 0 I over 2 pi r, and that's in the I hat direction. Actually, I just wrote it like it's in the J hat direction, and in fact I'm actually writing in red instead of black, so I don't like that either. So this is negative mu 0 I hat over 2 pi r, which is exactly the equation I just gave you as a rehash from the previous chapter. And notice that ultimately gives us the theta hat by symmetry. So by symmetry, B is equal to mu 0 I over 2 pi r in the theta hat direction for this particular orientation. So we just used the nasty Biot-Savart law to show us that mu zero I over 2 pi r is the magnetic field caused by a current carrying wire whose current is I and you're a distance r away. Any questions on that one? That's really a tough one, but notice it happened to be the same integral as what we did the first day in chapter 21. Except this one's nasty because it's got a cross product in the actual integral. So that's how you use the law, or one of the ways you can use the law of Biot-Savart. In fact, you can use this to calculate any magnetic field, but the rest, virtually all the problems you can solve, other than little arcs, all with the same center, basically has to take a numerical process. So you have to write computer code or something like that to work out the details of what the magnetic field is. But this gives you a way you could in principle do that. Any questions on that one? All right, let me show you another one real quick while we've got the time. What I'm going to do now is I am going to draw a coordinate system like this. This will be my x-axis. This will be my y-axis. And I am going to draw an arc. It's supposed to be a semicircle, in fact. It's going to be a semicircle that goes from here to here. That did not turn out as well as I'd like. I don't like it. I'm doing it again. Still don't like it. Close enough. Okay. So I'm going to imagine a current I going through this, and I'm going to say this distance from here to here is R1. And then I'm going to imagine that current hanging a left. And this distance right here is going to be R2 out to there. The current is still going to go that way, but now it's going to come back here and go this way. And then it's going to hang a left again and go this way. Okay. And what I'd like to know is, what is the magnetic field at that point? Okay. Now, what we can do is we can imagine very specific vectors. So right here, I'm going to make this my dl, and that's going to be r1 d theta. And that's going to point in the negative theta hat direction. Would be actually, yeah, that is a negative theta hat direction. So that's okay with that. And this vector right here is the vector RDL. The vector RP, on the other hand, is in fact zero vector because the P is at the origin. So this vector is RDL, and RP is equal to the zero vector. So RP minus RDL just turns out to be negative RDL, which is going to be basically negative R1 times R hat. So again, a vector pointing radially outward is our R hat vector as long as it's in the XY plane. So now I can say B is equal to the integral of dB, which is mu 0 I over 4 pi times the integral of negative R1 d theta theta hat cross negative R1 R hat, all that divided by the magnitude of RP minus RDL, which is clearly R1. So that's going to become R1 to the third power. Okay. So when I do theta hat cross R hat, something happens here. So I'm going to say B is equal to I'm going to pull out some of these constants. I'm going to say the negative mu 0 I, and I'm going to say this is R1 squared. Actually, notice there's two negatives, so I'm going to go ahead and make that a positive. And then all of this is divided by 4 pi times R1 cubed. So I'm just doing that inner arc right now. I've got all that. Now I have the integral of d theta times theta hat cross r hat. Now theta hat cross r hat is actually pointing out of the page. Yeah. And that out of the page is the k hat direction. So this right here is just k hat. If you want to see how that is, what you want to do is say, there's your theta hat, or actually your theta hat should technically be the other way. So let me fix that. Remember, we use negative theta hat. Oh, and this is R1. So theta hat should technically be this way. And then R hat would be this way. And now if I say theta hat cross R hat, I get one that goes into the board. So that's actually, because I forgot that it was theta hat was the other direction, that's actually supposed to be a negative k hat, not a positive k hat. K hat points out of the board. Out of the page anyways. So this one's going to be a complicated, nasty result, but I'm going to give you an easy way to do it every time you see it. And then you don't have to do this anymore, but you need to understand it so you can readily apply it. So now what I'm going to say is I'm going to have a negative mu 0 I. We can actually get rid of all but one of the R1s, and it's going to be 4 pi R1 in the bottom. And there's going to be a k hat right here. And then I just got to integrate d theta from theta equals 0 to pi over 2. Okay. So this is going to be equal to negative mu 0 I over 4 pi R1 times, now we're going to get pi over 2 times k hat. And you can see that that pi cancels out with this pi down here. And this 2 is going to make it an 8. So we get B due to the R1 is equal to negative mu 0 I over 8R1 k hat. Now, what this looks like is really, let's do it this way. In general, the arcs, as long as the arcs all have the same center, B is equal to plus or minus, you're going to say mu 0 I. The plus or minus just dictates which way you're going. So for instance, when you do the R2 radius one, that's going to cause a magnetic field that points out of the page, and that's the positive k hat direction. So you'd use a positive there. The one for R1, that actually pointed into the page, so you'd have to use a negative for that one. But either way, it's going to be mu 0 I over 4 pi R times the angle that the arc spread. So for instance, this one was an angle from 0 to pi over 2. It's a 90-degree angle. So you just plug in pi over 2 there, and you'd see that that would cancel out the pi and would give you the actual answer that we got, mu 0 over 8R1. So that's the general answer. Now I can say that B for R2 is going to be positive mu 0 I over 8 R2, and that's in the positive k hat direction. So I can say B total is equal to, the bigger one is going to be the negative one. So I'm going to say it's negative mu 0 I over 8 times, now I'm going to say 1 over R1 minus 1 over R2, and all that's in the k hat direction. Notice the negative going through is going to make the 1 over R2 positive, and the 1 over R1 is going to be negative, and that's completely the answer. Now, what happened for this little part, see this little part right here and this little part right here? Those little parts, okay, let's see. Those little parts don't count, and here's why. Straight lines contributed nothing because RP minus RDL is equal to 0 vector minus basically some R1 plus, well, let's do it this way. I'll just call it, come on now. That's just going to be some X I hat, which is negative X I hat. And then that's RP minus RDL, but DL is equal to DX I hat. So let's say DL cross RP minus RDL is equivalent to saying basically negative X dx times I hat cross I hat, and I hat cross I hat is 0. So whenever you have a line of current like this one right, actually if I can get a certain thing, like this one right here, if that line of current is parallel to the line connecting you to the point at which you wish to know the magnetic field, like this one is and like this one is, then the cross product's going to cancel out to 0, so you don't have to do anything with that. But that's the two applications of the law of Biot-Savart, and those are really the nastiest, hardest things you could possibly do in this 242 class. So I wouldn't worry too much about it, other than to be able to, I'm not going to get you to show me that you can work out all this integral, but now that I gave you the general formula for it, you should be able to apply that to any similar configuration, and that is fair game. So if you look in the end of the chapter, you'll see a bunch of different problems work like that. All right, it's now 7:50, so I'm going to go ahead and let you go. We have one more class meeting for you guys in 242. I see you there, Benedict. We still have one class meeting left. I will hit this and hit a couple other quick issues, but you really need to start watching the videos that I've posted. I'm going to post some more so you can see what all you missed, but there was some stuff where we covered the previous chapter, which was 27. And yes, so they're going to be that. And then there's another video you missed from chapter 29. I'll cover that, and then I'll cover just a little bit of 29 and 30 next time, and you'll be done. So you're free to go. Make sure you get all your tests done. Tomorrow's the deadline for all of them except for the last face-to-face test. The last face-to-face test can be taken tomorrow at 12 or as late as 12:45. You can't take any later than 12:45 tomorrow. or you can take it as late as 12:45 on Thursday, and I might even allow as late as 1 on Thursday, but that's about it. And if some people don't have any abilities to get over to me on those days, I could possibly figure out a way to get over here on Friday for you guys. So you're free to go. Let me know if you need me on Friday. If I have, one person that just can't do it except on Friday, then I'm going to do it. Or if I have several people that want to do it on Friday, then I'll show up as well. So have a good one. Thank you for coming. Bruce and Ethan and Ava, who was here earlier, but you're free to go. I'll wait for the last person to leave in case anybody has any questions.
When you say the last face-to-face test, are you talking about the final or like a fourth face-to-face
A
test?
fourth face-to-face. So what's happening is I managed to figure out a way to get us 4 face-to-face tests this semester. I'm only required to drop 1, but the whole reason for me getting 4 is I wouldn't feel too horrible since I've made you guys do all these tests over again. I wouldn't feel horrible if I considered dropping 2. So that's something I might actually do. I'm not required to because the syllabus did not say that, but it's something I'm considering if a certain number of people need help. That's probably what I'm going to do.
Can we take the fourth face-to-face online, or do we have to come to
Yeah, the
the
email I
other
sent out said
campus?
you can take it at home. Ideally, you do that with a mirror, but if you don't have a mirror, you can still try it. It's just there's some probability that I'm going to make you redo it because your eyes were looking in your lap too long, or your eyes were looking behind your monitor too long, which is, sort of one of the hallmarks of cheating. It also happens to be one of the hallmarks of, thinking. So it's really a bummer the way that works out, but that's what I have to do. So yeah, you're absolutely free to take it there. You're free to take it at a testing center, or you can take it at any of those times, like I just mentioned, or send in the email.
And that will be on chapters like 25,
It'll go up
26
through 28 for that one.
for test 4.
Yeah, for test 4. And the final should, in principle, go through 30. If I don't get this enough where I feel like you guys are comfortable, then I'm not going to test you beyond 28.
Okay. All right.
Okay.
Thank you.
No problem. How about you, Bruce? You have any questions? You cannot take the final at home, Bruce. That's the one thing is one, you can't skip the final. The final exam grade will not be dropped, and you have to take it face to face with a proctor. So your lab teacher has advised me that she's going to be there at 2:15 on Tuesday the 30th. So she can administer that for you guys. No problem. I appreciate you typing in the chat. I just happened to look at the chat and saw that you'd posted that. Do you have any other questions? Good deal. All right. See you, Bruce. Have a good one, bud. All right. How might I help you, Benedict?
So I retook the practice test, and there's one question I didn't get that I would like to go over, and there's a few from the chapter 9 quiz that I would want
Gotcha.
to go over. So, are you able to access my
Oh,
because
yeah.
my
Were you able to share your screen, or we find out you couldn't figure out how to do that last time?
I couldn't do it last time. I can try again if it's worth.
Yeah, give it another try.
Okay.
Let's see what happens.
Well, it says only the host can share in this meeting now.
Hold on a second. I got it now. Now give it a try. Looks like something might be happening.
Yeah, I don't see Canvas in this list of things I can share.
Do you see a screen that looks like the screen you're looking at?
What do you mean? Like,
When I do share screen, a bunch of little pictures of screens pop up, like 6 of them, and then
oh,
some of them are some other stuff. If you look in there, one of those is supposed to be the window that you're interested in sharing, and you just click on that, and then it'll share that one.
no, mine's just popping up saying select the where you want to share from, and it says like camera, screen, bookmark. Wait, I'll try screen. Turn it on.
Yeah, the screen should probably work.
It's displaying over other apps. I don't really know what that means, but it's loading. So, oh, wait, here.
What were the other
Yeah,
choices? I'll wait. It's not a big deal, but what were the other choices? You said screen and what else? Bookmarks?
yeah, it's like bookmarks and yeah, things like that, like photos and stuff. So I could take a photo of it and share it, I guess.
Yeah, even that's going to be a problem because it won't let you hand me a photo. Are you doing? I can actually go to your class though. That's what I'll do. I'll go to your class and from there I'll open up your tests and see if I can see it that way.
Okay. When you get there, it'll be attempt. It'll be the last attempt.
The last attempt on the
Or
9 through 11 one or whatever.
yeah, or attempt eight. Attempt eight. So
Gotcha.
yeah, for some reason, it's just taking me to like a list of apps that I can share, and Canvas is not one of them. So
Well, that's
what's
a
up?
bummer.
Yeah.
Okay, so I'm in there now and I'm looking for your practice test and I'm looking for your, there it is. Had to find your name too, that helps. All right. So I found 9, 10, and 11. I'm doing speed grader. And now I'm looking at the latest attempt, which was tonight at 7:29 or 7:21. And which problem are you thinking of? Number 9 or 8?
Yeah, number eight.
Okay. A 2 kilogram sphere is rotating about an axis through its center at 40.0 revolutions per second with an angular velocity in positive z direction. Okay. A torque of 10 Newton meters acts on the sphere about the center of the sphere in the positive x direction. What is the rate of change of angular momentum? Okay. So let me do a little drawing first, and then I'm going to steal the screen from you. But right now I need the screen to stay on your screen so I can understand what's going on while I draw it. So a 2 kilogram sphere is rotating about an axis through its center at 40 revolutions per second with an angular velocity in the z direction. Okay, so that means it's going counterclockwise from the positive x-axis to the positive y-axis sort of thing. So I'm going to draw my coordinate system. Just so I can keep my wits about me. And what I'm going to do now is draw the sphere like this. All right. I'm still working on it. The mass of the sphere, oops. The mass of the sphere is equal to 2.00 kilograms. The angular velocity is a vector omega, which points in the positive z direction, and its magnitude is 40.0 revolutions per second k hat. In the positive z direction. A torque of 10 Newton meters acts on the sphere about the center of the sphere in the positive x direction. So in that case, we're saying, let me give you a different color for this one. I don't think I want that. I don't think I want that. Let's say I do, I'm going to choose this color. So now what we're saying is there's going to be a torque coming out around the positive x-axis, which suggests that a rotation around the x-axis is that, and they want to know the rate of change of angular momentum of the sphere. So what they want is dl dt equals question mark. All right, so I think I have enough information now, so I'm going to share the screen. Okay, and you can see, of course, the correct answer is marked on my version of it. But the main thing is this green arrow is an arrow that you can pretends like the equator of the sphere, and that's the direction that the sphere is rotating. But now you're going to try to
It's still showing me the practice test screen.
oh crap. Okay. Oh duh. Yeah. I think I see why. There it is. Okay, I've got some problems. Hold on a second. Ah. Oh. It's not letting me pull down like I normally do. Let's see if I can pull up. Maybe that'll work. Nope, that didn't work. Nope, that didn't work. Oh, there you go. Finally, Jesus. Okay, so what we have is they want to know dLdt. What we know is the summation of the torques is actually equal to dLdt, and they specifically wanted to know what the rate of change of angular momentum of the sphere was. Okay, so the rate of change of angular momentum of the sphere is just the torque. So they said the torque was 10.0 newtons per meter, if I remember. Yes. Newton meters. Sorry, I don't know why I said newtons per meter. Newton meters, that's the torque.
Right.
Yeah, it's just, yeah, they gave you the answer. It's supposed to be really, really simple. It's 10 meters per 10.0 Newton meters I hat, which you can realize that a Newton is a kilogram meter per second squared. So a Newton meter is a kilogram meter squared per second squared. So you can also call it kilogram meter squared per second squared, and that's also it. But in this case, we already knew the torque and we knew it was pointing along the positive x-axis. So it's really just they're asking for the torque. So it's just 10 Newton meters.
Okay, that I guess that was. I was thinking it was.
Yeah, I was too initially. Then I looked at it, I'm like, oh, duh. Yeah, that's. I
Yeah,
thought I was going to do some really complicated crap, but no, it was really easy. You just have to read the torque and say that's specifically it. They even were fortunate. We're fortunate that it gave us a direction.
yeah. So I'm trying to understand the directions though from like what the I guess the instructions and what you drew. So when they say the when they say omega is going in the positive z direction, does that mean it's rotating in a positive z direction or the
That means
axis?
the right hand rule puts your thumb in the positive z direction.
Okay, and that would be the same for the torque.
Exactly. Yeah. So when you hold your right hand so that your thumb is pointing upwards along the z-axis, then your fingers are curling around the z-axis in the direction that the sphere is actually rotating. Similarly, when you talk about torque, If you say the torque is in the positive X direction, then you point the thumb of your right hand towards yourself and you see that it's rotating counterclockwise right in front of you. So that's how that works. You just put the right hand rule into place, and then the thumb gives you the torque or the angular velocity or the angular acceleration. They all are given by the direction of your right hand thumb.
So why is the x-axis towards me in this case? Isn't it normally where the y is and the y is where the x is?
You, as long as it's a right-handed coordinate system, you can make it any way you want. So if you'll notice, if you do your right hand, remember the right hand rule that's looked like this? This is one where you can actually hold the index finger and the middle finger at 90 degrees from each other, because what's supposed to happen is I hat's supposed to be your index finger, J hat is supposed to be your middle finger, and then K hat is supposed to be your thumb. So you can see if I put the x-axis pointing to me and the y-axis pointing to the right, then then clearly the k-axis is pointing upward. So as long as it's that kind of coordinate system, you're fine. But if you make a left-handed coordinate system, you are not fine. Bad things happen.
Okay. So then the torque is going in the opposite direction of the rotation in this case.
It's going at a perpendicular angle. They're trying to rotate it this way when it's rotating this way. It's already rotating this way, and they're trying to put a torque on it to rotate it this way.
Okay, so it was already rotating, and then the torque is applied after.
Right.
I was trying to figure that out. I couldn't tell from the wording or not.
Yes. So in my drawing, it shows you that the torque is along the z-axis. That means you should be, if you looked at along the x-axis, if you looked at the x-axis as if it's shooting right between your eyes, then you should imagine a little circle that's counterclockwise around that. That's the torque direction that they're applying. If, on the other hand, you look down along the z-axis, then you would see the same counterclockwise circle. In that case, that's the direction that the sphere is rotating.
So the change in angular momentum, wouldn't that be, is there no net torque on the sphere beforehand, I guess? It's just rotating.
There's no additional torque that we were given, so it's only the torque that they gave us is the only one we know of.
So that would be the summation of all the torques then, since that's the only one we have.
Exactly.
So then after that torque is applied, would it stop rotating in the other direction completely, or what would happen?
No, that would actually cause it to probably start to spin a little wonky. So it might actually spin at a diagonal or something like that.
Oh, okay.
Instead of completely horizontal, which it was doing, and completely vertical, which the torque is trying to make it do, it's probably going to be a combination of the two. So it goes like this at like a 45 degree or 30 degree angle or something.
Okay. But the fact that it's going in that direction doesn't really change the fact that the only torque on it is that one.
Exactly.
And so therefore the only momentum is going to be, or the only change in momentum is going to be that total torque.
Yep.
Yes.
So just remember that other form of Newton's second law. The summation of torque is dl dt. So when they ask you for the time rate of change of angular momentum, that's the same thing as asking for the total torque acting on it.
Well, it's kind of disappointing that it's all that, just they gave you the answer.
Yep. Yeah, it makes you feel like a bummer, but yeah, it's, could be worse. Could be a really hard problem.
Yeah, because would there be a way to work it out with the two like perpendicular rotations, or like
it would be very complicated. You'd have to do, it'd be nasty if you wanted to actually work out what the result is. But luckily that's sort of way beyond what we're doing, because that's going to be, you'd have to either analyze it for small amounts of time and then mechanically guess which direction each of those are using a string of right-hand rules and stuff like that, or you could analyze it numerically. But both of those are really tough to do.
Okay.
It's better to
Yeah.
just try it experimentally. Just, take a bowling ball to a bowling alley, get it spinning counterclockwise as seen from above. And then while it's spinning like that, try to twist it the other way and see what happens.
Yeah.
So if you start to tilt up like that, then all of a sudden it is going to take off down the aisle at some angle other than parallel to the lane.
Yeah. It would be. Yeah. I see. All right. So the other things were in chapter 9 practice. So
Mhm. So chapter 9. Oh yeah, I can't see anything on chapter 9 practice.
oh, you can't. Okay. Well, the first
Yeah,
one, I'm not even sure like if this one is even relevant or like because I thought the book said like aren't the asterisks on each like chapter section, don't those mean that it's
they're
not going?
optional. Yeah, and if it's normally a lot of the asterisk sections I omitted.
Okay, because it looks like
Okay.
this problem was from it. But I'll read it out to you and see if you think
Let
it's
me
something
see,
I
let
should
me
know.
see what you think.
So the question is a toy rocket has a mass of 300 grams and it takes off in the vertical direction.
Oh yeah, that's one of the rocket equations. I completely omitted that. I had a student ask me about that today. If that appears on your test, let me know because that's supposed to have been out of it. You're not supposed to have it on the practice test or anything. I
Okay,
didn't cover that, so you're not responsible for that at all.
all right, good.
Kind of a pain to try to do it. That's why I skipped it. It takes more time than I have in the summer.
Yeah. Okay. Well, that was everything for the first attempt. For the second
Mhm.
one, let's see, because I only did 2 attempts on this one. Okay, so it was just a conceptual one that I didn't really understand. It
Okay.
said, uh, identical forces act on the same length of time on two different masses, and the change in momentum in the smaller masses, and then they say, then there's like the answers.
Right.
So
So two objects have different masses, but identical forces are acting on them, and they're asking you about the
change
uh,
in
change in momentum. Well, the change in momentum is the integral of the force dt, so the integral of f dt. Uh, but the one with the smaller mass can have a bigger acceleration as a result of it, and that it can actually change the momentum more so than normal. But they might be trying to talk about. I'm trying to think of this. Actually, let me
both.
see if I can find that question. That might be the easiest way because I want to make sure I understand what's going on with it.
Okay.
I'm going to look at. Yeah, I'm gonna go into quizzes, and that's a chapter what? Chapter 9, maybe? All right,
Yeah,
9.
9.
Okay, I'm gonna go into the question banks, and I'm going to go specifically to chapter 9, conceptual. It's the first one in the test. In the
Yeah,
Okay, change in momentum. You got your no external, the impulse delivery, collisions in one dimension, and inelastic center of mass. What's the first words of it?
identical forces.
Okay, identical forces act for the same length of time on two different masses. The change in momentum for the smaller one, that actually should be larger.
Larger.
Yeah, let's see. Hold on. What it's saying is the correct answer is equal to the change in momentum of the larger mass. So they're actually saying it's equal.
Okay.
Now, the reason why that's so, let's see. Since they're talking about momentum, what you see is the summation of the forces. Let me show you on my tablet. So what we're looking at here is the summation of the forces is equal to dp dt. What that means is you can say dp is equal to the total forces times dt, and then you can say delta p equals the integral of dp from p initial to p final, and that's equal to the integral of the net force dt. By that alone, there's no place for you to actually put mass in, so there's no way to actually change it as a result of mass. So the change in momentum is evidently independent of mass here. The force is very much dependent on an acceleration in such a way that F equals ma is sort of a real thing from Newton's second law. So you'd think that it might make a larger acceleration, but what this is showing you here is that for a given force, it just depends on the force times dt. So the change in momentum should actually be the same for them.
So the momentum or the change in momentum, I guess, only depends on the force.
On the force and the duration of the application of the force.
Okay.
Because that's why you're integrating dt.
Yeah.
I was afraid that was going to happen, but I was hoping it wasn't. But then I realized it was chapter 9, so I figured it had to be.
Yeah.
Anything else?
So, hold on, I'm trying to just make sure I've got it right in my head. So the the only thing that's going to affect the force, or the only thing that's going to affect the change in momentum is the force.
The force and the time.
And time, yeah.
Yeah.
So it's kind of like because the torque is just the change in angular momentum.
Right.
So it would only depend on those two.
Yeah, in this case, it wasn't the angular momentum, it was the linear momentum, but I understood what you were saying.
Oh, it is linear. Oh, okay. But it would be the same for both, right?
Mm-hmm.
Okay. All right. Well, I guess that's it for now. I don't really have any more questions that I've gotten wrong yet. So
Okay. No problem.
yeah, I mean, I'll see you tomorrow. I'll have more by then, hopefully.
All right. No problem. Have a good one, Benedict.
All right. Thank you.
You're welcome. All right, so I guess that's it. Stop sharing. End.